Today, we're joined by the renowned astronomer and my good friend, Dr. Robert Kirshner. Robert's the executive director of the 30-meter telescope, a remarkable international scientific endeavor that will radically change our understanding of the cosmos and our place within it. Robert's one of the few people who can rightly say he proved Einstein wrong when he discovered with his team members, including past guest Adam Rees and Brian Schmidt, that the universe did have a cosmological constant, unlike old Albert, who claimed that dark energy, or the cosmological constant, was his biggest blunder. With its unprecedented design, the TMT will feature unique capabilities for exploring black holes, giant galaxies, dark matter, and the possibility of life outside of our solar system. In this exciting episode, Robert shares the ambitions of the TMT and takes us through the historic past and present and his role in the creation of our modern cosmological model. He's mentored not one, but two Nobel Prize winners, and you're going to be in for a treat with his mentorship as well. So tune in. I know you're going to enjoy it. Now, let's go into the impossible. Bob, how are you doing today up in Pasadena?
I'm delighted to delighted to be here, and I haven't seen you in a while, so it's fun to catch up. And I'm ready for whatever you've got cooking here.
The very first thing we always do with our treasured guests is to do something you're never supposed to do, which is to judge a book by its cover. When I was preparing for the interview, I looked back, to cut and paste in all the details of your work and your vast career that has really been 10 careers worth, just incredible output. And I look back and I went to Amazon, it's the only place to get books. And it said that I bought your book in May of 2003. So my copy is over 20 years old. I understand there's been recent additions, but Bob, help us. Judge a book by its cover. Tell us the title, the subtitle, and the cover art, and what it should evoke in the eyes and mind of our listeners and readers.
Well, all right. First of all, authors don't get to choose the way their books get packaged up, but I'll take it. This is the current edition. They've cheaped out on the photographs. There are not as many color ones, and the print's a little smaller. But anyway, it's pretty good still in print. You can get it from Princeton University Press. It's called The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos. And then we've subtly put here a picture of supernova 1987A, which is not the kind of supernova that we use to measure the distances and see about the accelerator, but it's a very good space telescope image of kind of a mysterious place that you might want to learn more about. So that's the hope, that somebody will pick this up and be intrigued by the cover. I will say that I have actually been in a bookstore where somebody picked up the book and put it back. Oh, I didn't know what to feel. I just walked out of the room. I couldn't handle it.
Speaking of emotions, I've had on your mentees, Mentos. No, that's the mint. I've had on your mentees, Brian Schmidt and Adam Rees. And I've also, the only person I haven't talked to in this field is Saul Perlmutter. We're going to get to that in just a bit. Why he's freezing me out, I don't know. There's a quote that came out, and I remember reading it. I was back at Brown University giving a colloquium. I was returning hero on October 10th, 2011. And it was great on a Monday, and I was feeling high. I brought my wife and my son. And the next day, wake up, and there's news that Adam Rees and Brian Schmidt and Saul Perlmutter had won the 2011 Nobel Prize in Physics. And I don't know if you know this, Adam and I have joked about this many times, but there was a competition held in 2005 at Berkeley to identify future scientists that would come to be as prominent as Charlie Towns. It was the 90th birthday of Charlie Towns in 2005. And it was supposed to be breakthroughs that would amount to breakthroughs significant like the Nobel Prize worthy discoveries that Charlie won. Anyway, I ended up winning that competition. And Adam came in third place. So on that day in October 2011, my older brother, as only older brothers can do, I love him so much, called me up and said, Brian, you may have won the battle, but Adam won the war. I remember taking some comfort in the statement that you said the following on that day. What's the strongest force in the universe? It's not gravity, it's jealousy. What did you mean by that?
Oh, well, I was alluding to the other team. I thought, they had been very vigorous about promoting the work that they had done. And I thought, man, somebody's got to speak up for Adam and for Brian, well, and for me too, but somebody's got to do that job. And so I thought they were jealous of us, is what I really meant. And, but what I meant really is people care a lot about what they do, and they're put their whole selves into it. Adam is notorious for this, and it's really mostly a good quality to care so much and to be so alert to what the currents are flowing back and forth. So, there was a lot of discussion in the press about the road to the discovering cosmic acceleration, and I thought it was really important for us to say clearly what we had done. Mm-hmm. And that's why I wrote the book too, is to, before I forgot, to write those things down. So even though Amazon is telling you it was 20 years ago, the words in the book haven't changed. It's only your memory that decays slightly. But I will say something about writing the book too, which is that I thought I remembered everything clearly. And so when I finally got the manuscript written, I sent it around to Adam and Brian and, I don't know, Mark Phillip. I sent it around to people, Filipenko, I sent it around to our team. And they came back with some very clear differences. They said, no, that's not exactly how it happened. This happened before that, or I was there and you weren't. And a lot of things that in your mind, you put all this stuff together into a picture or a story, and you have to check out the actual documentary stuff. That's the difference, I think, between journalism and history. Journalism, they can ask people what they think today. History, you actually have to look at the documents and see when they were published and what they said, because it does get a little blurred up in people's minds.
Hey there, fellow explorers of the impossible. As we continue the celestial journey, I have a tiny favor to ask of you, which is that I'd be so delighted if you'd actually consider subscribing or following this audio podcast, wherever you're watching or listening to it, on YouTube or on audio. We're sitting at only 18% of you out there that are actually subscribed, but you're obviously enjoying the content. Let's change that, shall we? By subscribing, you'll be the first to know about the frontiers of knowledge and hear from great minds just like Dr. Kirshner as you're learning about and enjoying today. So join the best community on Earth, or maybe in the entire universe. Don't be shy. Hit that subscribe button, give it a tap, and now back to the episode. Oh, yes, the constant conflation and inflation. We'll get to inflation.
Yeah.
That's the strongest force, is conflation. So let's take us back. Let's take a bigger step back out of the petty realm of the sociological and the quotidian. Let's go back to your mindset as a physicist of eminent reputation and accomplishment in the 90s. You were not looking for this. You commissioned this survey and were advising these other brilliant scientists on effectively not intending at all to discover what you did. And in fact, I think trying to discover the opposite, namely that the universe was decelerating. How did it feel to be proven so wrong, but in such a delightful way?
If you asked somebody in 1987 or some other time, what was the most likely story for the large-scale structure of the universe and the history of cosmic expansion, it would have been, because the theorists told you so, that the universe was in this just balanced state where there was enough matter in the universe so that the universe would expand, but always slow down, and that's it. Not collapse again, just slow down, slower and slower as time goes by. And we thought we could measure that. Once we got going on how to use the supernovae as distance measurement tools, if you had enough of these at a reasonable time in the past, or distance, so same thing, then you would be able to detect this effect of slowing down. That seemed like a good thing to do. Everybody wanted to do it. The odds on, if you ask people, as I said, were that it was going to be, omega equals 1, that is, a universe that was just bound. And that was kind of interesting because when we did measurements, when I was involved in some of them, of galaxy clusters, where you measure how the galaxies are moving and you infer how much mass is in there, or you look at the X-rays from those clusters. You didn't get the same answer. You got an answer of about 1/3 in those units. And I remember, this is more back to the sociological, but being at a scientific meeting, and one of the theorists who thought they knew what the universe was like, coming and kind of leaning over me a little bit and saying, that's a pretty hard measurement, isn't it? And I said, well, yeah, of course, it's a hard measurement. And there's some uncertainties in it, aren't there? I said, well, yeah, sure, of course. We're doing our best, but. And so it was funny because people did not want to hear that. They did not want to hear that the density was low. The problem with the low density was that if the universe had been expanding according to that trajectory, where it didn't slow down, basically, you get a certain age for the universe based on its current expansion. And that age did not match up with the age of the stars. So this is really bad. It's not good to have things in the universe that are older than the history of cosmic expansion. That just didn't sound right.
That's like when your stepmother is younger than you.
There you go. So so the trick is, of course, to figure out how to have both of those things at the same time. And we all knew what the answer was, but we didn't want to open this closet because it had in it the skeleton. It had the cosmological constant. This was the thing that Einstein allegedly said was his greatest mistake. It certainly was something he didn't want to talk about after people figured out that the universe was expanding. But it was something he had put in by hand early in the history of general relativity to make a model of the universe that would be static. And he thought that'd be good. You got mass pulling in, you got this other thing pushing out, and you could make it static. Well, other people pointed out some defects with that. It was maybe static, but unstable, it would either go one way or the other, and not really a very satisfactory thing. And when Hubble and others started to show that we live in an expanding universe, Einstein was pretty quick to back away from the cosmological constant. So it required a very bad reputation as the kind of the idea that only rascals would advocate. As we got closer, as the data got better and better, people began to think, hey, how are we going to get this straightened out? If we know the current rate of expansion, and we know the history of expansion, you can figure out what the age ought to be. And it was quite discrepant for the age of the stars. Now, of course, they don't come with little mint marks on them that tell you exactly when they were formed, but we have a pretty good idea how long a star lasts and how it changes over time. And we have a good understanding of that. And people then began to think, well, I guess we need a crazy idea. And there were at least a few papers. Jerry Oestreicher wrote a paper. He's a more or less reputable fellow, and others who said, well, you could get a solution if you allowed this universe that was accelerating. So the current rate of expansion is not equal to the rate of expansion over time. And, that seemed like, well, okay, but nobody wanted to go there, as far as I could tell. And some people said, well, it must be that you've measured the rate of expansion wrong. The Hubble constant is wrong, like by a lot. And we had just gone through an agonizing history of kind of getting it more or less right from the days back in the 60s and 70s and into the 80s, where Gérard de Vaucouleurs and the Texas people got a value of 100 in the usual units, and Alan Sandage and Gustav Tammann got 50 in the same units, and they just kept getting the same numbers as time went by. It was really kind of embarrassing that there was such a big discrepancy about such an important thing, but that sort of got straightened out in the early 90s with the advent of the Hubble Space Telescope and the ability to measure some of the standard candles, the standard way with Cepheid variables to measure the distances to galaxies. So we expected to find a low-density universe or a high-density universe, and we could tell the difference from this history of cosmic expansion. And as the data started to come in, it was a little peculiar. We thought, well, are we doing something wrong? The other guys, the LBL, the Sol Perlmutter's group, had published a paper before we published our paper. They published a paper that said, it looks like things are slowing down. And I thought, oh, okay. And that made it harder for us when the time came to, when we began to see that our data was not pointing in that direction. And so we were using this, yeah, similar. Yeah, we were using mostly the same Yes, we were using mostly the same telescopes. But it's not the telescope that makes the measurement. It's the person looking at the data who makes the measurement. And I thought, well, I know, we had a really good team of people who were very skilled at this arcane art of photometry, of measuring the brightness of a faint thing. Anyway, we had a really good team. We had, for example, Nick Sunsef was on our team. Nick Sunsef is kind of a Eeyore type. Things are, oh, gee, this isn't right, and I got to check that. And that's also a very valuable kind of personality to have in your team. At first it sounds kind of annoying, but it's not. It's not. It's really important to have somebody who doesn't just take things at face value and who asks, well, did you really check this? And have you compared it to that? And we had a lot of confidence that we knew how to do the measurements. We also had, in those early days, we had more data from the Hubble Space Telescope, which was very valuable, and we knew how to use that too, because we'd been doing that for other things. I think in the end, we were more confident that we had made a real measurement, and eventually we said that in public, while the other guys were still saying, well, we have to analyze how the dust affects it. And, we wrote a paper, which is the paper that really is cited for the Nobel Prize, that was sent in early one year. And it was actually, how publication is, it takes some months to come out. And ours came out before the other guys submitted theirs. So, in the cosmic history, it's a small thing, a few months. But to us, it's kind of important. And we made the effort to double check things because, we were kind of contradicting what the other guys had said. So that was an extra burden on us, and it made us a little more cautious. I got to say, I was the one who slowed things down the most. There was we had a big call back and forth. I think in the book, there's some of the emails are there. And I said, if this is really the cosmological constant, it's really a terrible thing. And the kids, of course, said, hey, come on, look at the data. Here's what it shows. So part of it is the baggage that you carry. From graduate school, it had been a very unsavory thing to talk about the cosmological constant. But it looked like we needed it to really fit our data. And of course, it's very important because if it's the kind of thing that we measure now, it's about 2/3 of the universe is the energy density of the universe is in this funny stuff that powers the expansion, that basically has a negative pressure. It wants to expand. So that's a funny kind of thing. It's very important, of course, because if it's most of the universe and it's not predicted by the standard model of physics, this is a big new thing. And so it was important. It is important. And I guess what's surprising to me a little bit is that although there's been a lot of great work on baryon oscillations and the connection from the cosmic microwave background is really great with one sort of loose end, two actually, but the picture is really, really good for an expanding universe that has this extra term in it. But the understanding of it has not improved much in 20 years. So that is an interesting thing. I started out by talking about sort of a theoretical idea that the matter would dominate the universe, and then people said, "Oh, well, that can't be right." So, so now, we have this cosmological term, but there's no fundamental understanding of it. If you take, if you punch a theoretical physicist on the arm and you give them an envelope and a pencil, and you say, "What do you think is the value for the vacuum energy?" They'd say, "Well, I know what the Planck length is, so I guess it's 1 over that to the fourth power." And you get an answer that is wrong by, 10 to the 120th, not by 10 or by 120, but 10 to the 120th, which is surely the worst quantitative agreement in all of physical science. Something's missing from our understanding, that's for sure. And it's why people have been so energetic at pursuing the dark energy as a topic. And people have built experiments that are focused on, and satellites that are focused on the question of what is the dark energy? How has it changed over time? The one that just got launched, Euclid, the European satellite, is aimed at doing some of that. And the Roman satellite that, the one where we took the spy satellite and took all the spy stuff out and turned it so it points up, the world's most expensive free telescope, as it's referred to by the people who work on it, that has as important part of its mission elucidating the nature of the dark energy. And of course, the dark energy and the dark matter make up most of the universe. And it's fair to say we do not know what they are. So I kind of like it that we have such a good reservoir of ignorance. It means, there's a lot more to be learned. And you should just be open-minded, maybe more open-minded than I was in 1990. You should be open-minded and humble about it because, people like to tell you how complete our picture of matter is. And there's no doubt about it, the Standard Model is a great thing, and it predicts a lot. But it doesn't predict the dark matter, or anyway, we don't know what the connection to dark matter is, and it doesn't predict the dark energy, this cosmological constant or negative pressure, the thing that's making the universe accelerate. So we ought to be humble about that, and eager for new ideas and new measurements.
Yeah, and how we can balance the swagger that you need to be a good cosmologist with the humility that it takes. Yeah, I always say it's too bad that Einstein was wrong about that blunder not being a blunder. He even his blunders were blunders, right? Because otherwise he could have had a good career.
Yeah, he could have had a good career. Yeah.
I see on the back you've got your Wolf Prize certificate. I read.
Yeah, I do. Hebrew. I know you can read it.
Kirshner, yeah, I can read that. I can read a little Hebrew, a little Aramaic here. Yeah, and they offered Einstein the presidency of Israel the early days.
Yeah, that would have been a mistake.
He declined it, but can you imagine what kind of a career he could have had?
No. Yeah, the Wolf Prize was really fun. They're they like to think they're predicting who will get the Nobel Prize. Well, this was a little too late for that, and I got it the same year as B.J. Bjorken, who did the scaling models for the electron. Well, basically showing their quarks in matter. And he didn't get the prize. The experimentalists, who are also wonderful people, got the prize. So it was a little bit the year of consolation prizes, not a prediction.
No, exactly. But that's okay. We should have kind of the perspective that all Nobel Prize winners always have is, the Nobel Prize wasn't a big deal. I just talked to Kip Thorne as I was remarking before we started recording, and and he said, it was the only thing that he really resents and regrets is that the Nobel Prize didn't go to everyone on LIGO. And I said, well, you didn't have to accept it. People act like, it was forced on him. He had to guzzle it down or something like that. But anyway,
Bob Dylan didn't show up.
That's right. Oh, yeah, that's right. But no one has ever rejected the Nobel Prize in physics. I think it's the only one. The Peace Prize many times has been rejected, even the medicine prizes. But everyone and even Feynman, your old buddy and mentor, probably Richard Feynman, he used to say things like very contradictory. He'd say, I drilled a hole in mine and made a necklace out. He didn't do that. That was all made up. But he would say you should be able to explain it in terms that even your grandmother could understand. And then when the day he won the Nobel Prize, some reporter asked him there in Pasadena, what did you win it for? And he said, "Hey, bud, if it was worth a Nobel Prize, I couldn't explain it to you." Uh, so
Well, he was not always a totally consistent
no, he was not.
person.
So I want to pivot back. I like that term, reservoir of ignorance. I
Yeah.
think people have called me that when I'm swimming in a bathtub. They speak about my but we'll talk about the kind of balance between when Einstein was right, as he was several times, obviously. He had great kind of confidence when he said allegedly on the discovery of the gravitational deflection of starlight behind the sun during the 1919 eclipse. He said, when asked, what if it had been proven wrong? He said, well, then I would have felt sorry for God because my equations were right. But by the way, you and I know this, but 5 years earlier, the equations were wrong. He had a missing factor of 2. So if World War I weren't going on at the same time as the eclipse of 1914, he would have been proven wrong, and he would have really been concerned about good old God. But then later, he came up with many other sort of silly ideas and many blunders along the way. So I wonder, how do you balance that? When you're approaching grand questions, before which you have to approach with the trepidation, you may drown in the reservoir of ignorance. How do you balance that with the kind of confidence that it takes as a observer or theorist or experimentalist like me, to go forth when it seems like the arrayed armies of nature are myriad and will certainly lead to your defeat? How do you have the confidence to proceed in such situations?
Well, I think a lowbrow approach is good for some of us. We're working on advancing the frontier of the technology, and that creates opportunities. You do it, your motivation is these big ideas. The actual doing of it is very detailed. And the application of it is, you try to pick the lowest hanging fruit, things that you can do now that you couldn't do in the past. And so, I'm embarked on that now for this 30-meter telescope. The idea is there are some very important things we'd like to know about. We'd like to know about what the planets are like around other stars. We'd like to know about how the universe got ionized. You know that happened. But exactly how did it happen? What stars did it? Or black holes, did they do it? How did the galaxies form? And what we see, for example, with JWST, the new space telescope, is that not everything we were saying with such confidence a few years ago, or 2 years ago, is really correct. And that the improved instrumentation, which people beat their brains out to build, is really performing extremely well and narrowing down some of the questions, and at the same time, lifting up some of the questions. So we had a meeting at UCLA last week about, okay, we're talking about building these 30-meter telescopes and so on. The underlying question was, why bother if you've got JWST? If you have that big telescope in space, how come you're doing all this hard work on the ground? And of course, the answer is that the big telescope in space is not that big. It's 6.5 meters. We're talking about 30 meters. And that there are two things that go on when the telescope gets big. You collect more light by the area, but you also, if you can make it operate at the diffraction limit, the limit set by the wavelength of light and the size of the telescope, the images get smaller, which is very good. So the big telescopes are really these extremely large telescopes, are going to have 4 times the resolution, so the images are sharper by a factor of 4 in each direction. Ooh, that's very good. And that you're going to collect a lot more light. It turns out that the scientific questions that this can illuminate are very broad, but I just mentioned a couple of them. The exoplanets, you'd really like to know what their atmospheres are. Was there some sign of some algae exhaling oxygen or something like that in the atmosphere? And JWST is great at finding the planets. And it's hard to do some of the analysis. So the big telescopes are going to have high dispersion spectrographs. So that means they can spread the light out to very, very fine detail. And that turns out to be really valuable for seeing what molecules are in the atmosphere of a planet. So there's going to be a big role for the big telescopes to do that. Another item, you heard, there's lots of galaxies early on are much bigger than we thought. Well, some of them are bigger. We'll see what fraction of the population it is. But the question of how, when galaxies form, it seems like they always form with a black hole. That's very interesting. We don't know which is the chicken and which is the egg exactly. But anyway, the black hole and the galaxies are associated with each other for sure. And we also know, because this is what the microwave background is telling us, is that the universe used to be opaque and neutral. And now we know it's ionized. The gas is lost, the electrons are separated from the atoms in the gas. So there was a time when that happened. And there was a cause of that happening, and it's got to be the galaxy formation, broadly put. But was it the stars in the galaxy? Was it the black holes in the galaxy? And if you have a galaxy with that's got an ionizing source in it, either from hot stars or from a black hole, the galaxy is kind of opaque too. So most of it doesn't leak out. So learning how much leaks out, it turns out, is kind of the key to understanding this huge physical process that changed the universe. And for that, the ground-based telescopes are excellent because you want the blue end of the spectrum, which is where the ultraviolet light being emitted from these high redshift guys is. There are some places where JWST is not closing things off. It's opening things up. And then there are places where it's exactly the right thing, like the center of our galaxy and some other galaxies. But in the center of our galaxies, as you know, there's a black hole in there, and with adaptive optics, which is the other big technical trick here, with adaptive optics that take out the wiggles of the Earth's atmosphere, you can see individual stars that are in the neighborhood of that black hole. And if you're diligent, as Andrea Ghez has been, and you measure year after year after year where those stars are, you can actually see their orbits. And it's a phenomenal thing. It allows you to know that there's really a black hole there, you know its mass, and they're kind of closing in on even more interesting questions. Now, Andrea got the Nobel Prize for this work. She shared that. And it was with Reinhard Genzel, and it's a great thing to be able to measure. But we know we can do better. If you have a telescope that has better resolution, it's very crowded in there, many stars, you can't tell which is which, and it's all kind of a blur, even at the current level of adaptive optics. You can do better than that, and you can see, you're sensitive, so you can see more stars. You can make a much more detailed study of the gravity of a black hole, and you can even begin to start to test general relativity, some aspects of general relativity. You can find out if it's rotating. There's a lot of stuff you can do. These big telescopes are not going to be put on the shelf because JWST is doing such a great job. It's the other way around. JWST is really going to help.
Hey there, fellow magicians traveling into the impossible. It's your favorite professor, Brian Keating. For the brightest among you, I invite you to my masterclass, preparing a fun set of extracurricular activities. And to access them, all you have to do is go to briankeating.com/list and join my mailing list. And there you'll get incredible resources for learning more about the cosmos and our special guests. I'll also tune you into what's going on in my laboratory, in my life, and the various appearances and genius items that we're discovering from around the world. I call it my Monday Magic Messages, as I share a musing, an appearance of mine, something genius that I've discovered from around the world of STEM, an image, a beautiful astronomical image, and a conversation from the previous week's Into the Impossible podcast. And you'll get some extra credit. If you do join, you may win a meteorite, a real 4.3 billion year old chunk of space schmutz that I've collected and will send to one of you lucky subscribers to the Monday Magic mailing list. Each month I choose somebody at random to win, but you're guaranteed to win if you have a .edu email address and you live in the United States. I'll send you one of these beauties that's 4 billion year old plus chunk of dust in our early solar system's history. Now back to the episode. Don't forget to visit briankeating.com/list. There is a percolation in the zeitgeist claiming that because of the images revealed by the JWST deep field, these images reveal galaxies that are just simply too mature for them to have been created in the mere 380 million years imputed from their redshift. And this is allegedly causing crisis for the Big Bang. In fact, some suggest the Big Bang may have happened 26 billion years ago. And some go so far as to say the Big Bang never happened. What do you make of these claims?
The right thing to say is it has been surprising how well JWST has been able to study these redshift 12 or whatever it is galaxies. It's really impressive. And the telescope, of course, was designed to do that. I was on the Dressler Committee, which was the group that said, what should we do after the Hubble Space Telescope? And that was 1996, I don't know, somewhere in there. And we thought, well, you should build a big, cold, infrared telescope in space. And we were talking about an 8-meter, and that turns out to be even harder. 6.5 meters, made of individual hexagons, the way the Keck telescope, the 10-meter telescope is made, and the way the TMT is going to be made, is a really good idea. You can, and of course they did this genius thing of folding it up so it could fit into the rocket. And it works great. It works great. It does what it's supposed to do, and it's measuring these high redshift galaxies. You are right. What's seen is more of them than people expected. So the question is, what's going on? And surely the problem is people were expecting the wrong thing. That is, the details of how galaxies get going. And for example, you can find what the average number of these galaxies is. Not very well yet because the numbers are small, but you can find what the average number is. But it's pretty likely that these galaxies have spikes of brightness, that they're not very big, and so a few really big stars makes a big difference. So I think it's more a matter of not understanding properly the nature of the galaxies and the way galaxy formation takes place. So I think the people who have gone past that to say, well, maybe the whole expanding universe picture is, bad or miscalculated or something. I really think that is not justified in this case. That what we see, it is surprising, it is interesting, and it does. Whenever you're wrong, that's when you learn something. And so in this case, the models are wrong, but on average wrong, and the deviations from the average may be pretty big. And so when you take all that into account, it's maybe not so surprising that we see these galaxies at the high redshift. So with such high luminosity. So that is still talk, and getting the real measurements of those galaxies is going to be a project. JWST can do some, but you're going to need these really big telescopes. What we've learned, and that has sort of gotten lost in the discussion, is that the extent of the galaxies, the size of the galaxies, is small. Those early galaxies are small. And that means you are not resolving them with JWST. You're seeing all the light kind of blurred together. But with big telescopes, with TMT, for example, you're going to do 4 times better in each direction. And you'll have a kind of a real picture of the galaxy. And you'll see, is it lumpy or is it smooth? You'll be able to say something that might be a clue to what's going on in that galaxy. And I think the business of Surprises is good. It's an important thing. And if you want to know how galaxies form, you're going to learn something from it and improve our understanding. So I think that's the right way to regard those measurements.
Let's go back to TMT. So this project, I was going to say, how big is it? Like those folks that call up 7-Eleven and ask what their hours are, right? So 30-meter telescope is poised to be the biggest telescope on Earth when it's constructed. And I want to get an update because I was in Chile in 2019 for the Great South American Solar Eclipse. And I visited the GMTO, Giant Magellan Telescope, which is also headquartered in Pasadena. So I don't know how you guys share, this 1 square mile, of California real estate. It's even more contentious than, Barbara Streisand's air rights. But what is the purpose of having another giant telescope, even more gianter than the 24, 25, 26 meter GMTO? Why do we need two of these things if, resources are finite and do they not have an insurmountable edge? I have to give some provocative, I have to provoke you a little bit because I know you can handle it. But they're putting mirrors up pretty soon. Where are you guys? And does the world really need two telescopes? Explain why.
Let's get the whole context. There's the US and there's the rest of the world, which in this case is Europe. So it's the European Southern Observatory, which is building an even bigger telescope, the 39-meter telescope, extremely large, European, extremely large telescope in Chile, at a site north of Las Campanas where the GMT is going to go. So they're building a much bigger telescope in the southern hemisphere, the same hemisphere that GMT has chosen. The overlap between those two is going to be significant. They're, of course, each going to have their virtues and special things that each of them can do. But I think the right perspective is to say, well, what does the U.S. need to do? And we've been the leaders in observational astronomy for 100 years. It's Mount Wilson and so on. And are we ready to say, well, okay, the Europeans will have the leading telescope and we'll be, active spectators and participants and, I don't know. This happened in particle physics, of course, where the U.S., which had been the leader, or anyway, had been the leader, is fair to say, was building the super collider, superconducting super collider, and then Clinton decided not to do it. And that has had a long-term effect on that field of science where leadership passed to Europe. Now, your particle physics friends are energetic and they work with International Collider and so on, but it's not the same thing as the Americans being in the lead. So what we think you need to do, what we think the National Science Foundation should do, what the Astro 2020 Decadal said the National Science Foundation should do, is think about a program north and south, 30-meter in the north, GMT in the south, that would be available to U.S. astronomers, even if they're not at the institutions that have put up the funds to build these telescopes. That is, the NSF would have a national share that everybody could use, and then it would just be on the merit of your proposal. That seems like a very good idea, that the U.S. would have parity with Europe and a real opportunity for our very lively community to do the science they want to do. So you'd have two telescopes, a share of two telescopes, northern hemisphere and southern hemisphere. So there are parts of the sky that you cannot see from Chile, as you know, and parts of the sky you cannot see from the northern hemisphere. But if you have both, that means even if there's some very rare thing, like a planet around a star that's very near and really interesting, you don't know whether that's going to be in the north or in the south. Or what if LIGO finds an event and you want to go look to see what's there, Well, the Earth is transparent to gravitational waves, but is not transparent to light. And so you need a facility, you need access to the whole sky. And what we've learned from those LIGO events, or from the colliding neutron star event, is it's faint and it's fast. So you need to be able to get right on it and study it while it's still emitting light. If you have two telescopes, if they're let's say in Hawaii and in the southern hemisphere, Las Campanas, they're different in longitude by some considerable number of hours. You know, Chile is like east of Florida, not south of Florida. So that means you can keep your, if there's some sudden transient thing, you can keep it in view from the south, from the east, and from the western parts of your team for quite a while. So those are really good things. You'll have different instruments. You'll have twice as many nights. There are a lot of good things about it. And, one might be cloudy, one might be clear. There might be opportunities that would be lost if you only had one. So that's our current plan. And I hope that we'll have the courage to carry through on it. It is an expensive plan, but, this is money that would be spent over a decade, and it would last for 50 years. So I don't think we should be ready to give up on the future generations yet, and we should really take seriously this idea of a US ELT program, a joint program of the two telescopes. And that's how we've presented ourselves to the National Science Foundation. They say, well, we'll take you one at a time. Okay. And we're hopeful that this will have a good result. Boundaries will come from financial constraints. And it's a question of how much the country wants to invest in basic science, how much the country wants to advance the frontier of technology. And I think this is a good bargain because the other half of the money for each of the telescopes has already been subscribed by international partners and by universities. So it's a real opportunity for the NSF to really do something great.
And so, what is the status of TMT? And maybe you could talk a little bit about the controversy, obviously, on the siting of it. So it has become sort of a massive controversy with site considerations, cultural, environmental impact with respect to its proposed original location of Mauna Kea. I recall there was, I'm working with Gary Sanders here at UC San Diego. He listens to all these podcasts. He sends you his regards. But the question of exactly where it'll be sited seems to be a pretty basic thing. And I guess my viewers might be surprised to learn about the current status. So can you
Yeah,
talk about the siting and prospects for it to
yeah.
be deployed in the near term?
Yes, those are very good questions. So first of all, we've made really good progress on the technical side. That is, we're not just sitting on our hands. It is true that the project construction was halted by protests in 2019. But that doesn't mean there isn't something to do. We are making the mirrors. We need 492 mirrors, and we're approaching 100. So, we're on the road. We're not there yet. Our Indian colleagues have built up a production line for mirrors that is the same as the production line in California that we're currently using. And that is at a place that did the mirrors for the 10-meter Keck telescope, that did the mirrors for JWST. They're doing our mirrors. That's the A team, and they're working on our stuff. So the technical things are progressing well. The National Science Foundation has said, yeah, this is a good kind of project, as the Astro 2020 decadal told them. And so they have gone forward now to provide design and development money to us. So we got $6.5 million in 2023. So that's good. Also GMT got money and the national labs to help with other aspects of the project. So that part, we're making progress. Now, what about the site? Fair enough. This is a real problem where we are really taking a different approach now. The cultural importance of that mountain is something that, well, we learned the hard way, but also that we really have absorbed. And now we're spending a lot of our time and effort talking to people, listening to people, building relationships in the community. So it's a different kind of story. It's a community astronomy story. If you read the Decadal, it has a whole chapter about community astronomy, and you have to do more than just lip service. You have to actually take the time to listen to people, and we're doing it. Feng Xuan Liu, who's our project manager now, is living in Hilo in Hawaii, and we have a staff there, and they are spending a significant amount of their time going out and listening to people. Now, the easy people to listen to are your allies. You know, there are plenty of people in Hawaii who think it's a great idea and are in favor of it, and we want to talk to them too. So we do. But the opponents are people who care deeply about the mountain. They care deeply about their families. They have been treated, the Native Hawaiians generally have been treated very poorly by the U.S. government, and they're very mistrustful of it and of the state of Hawaii. So, you know, the real issues are things like housing, healthcare, education, big stuff that the telescope is not going to address directly. But there are things we can do. For example, we talked to the schools in Hilo, and during the pandemic, they weren't having school, and a lot of the kids in the rural areas do not have access to Wi-Fi. So the kids are really falling behind and not doing very well. And so we have helped with a tutoring program. So we do one-on-one tutoring with kids. We make sure they don't fail eighth grade math. Now this turns out not to be too challenging for some of our engineers, but it's the personal part. It's not the math part that is important. And we've really tried to reach out to make contact with people to show them that we're different than we were, and we really are going to go another path. So, for example, people who were arrested, you know, there was a very dramatic scene there on the access road to Mauna Kea. Elders were arrested. And for quite some time, you know, this is very divisive. They didn't want to talk to us at all. And I would say now we are making considerable progress talking to some people who have been our opponents. And, you know, you're not going to persuade people right away that this is more important than something else. But they begin to see you as not the enemy. And there is now in the state of Hawaii a new way of running the mountain. The mountain had formerly the astronomical precinct up at the top, and a lot more of the mountain too, was run by the University of Hawaii. That accumulated a certain kind of resentment among the people in Hawaii, that somehow it was a benefit to the university and to the astronomers, but not a widely spread benefit. And the state has initiated a new regime where they have the Mauna Kea Stewardship and Oversight Authority. It's a new thing that's going to have the right to give the leases for the telescopes and so on. It has Native Hawaiians on it. So that's a vehicle for their voice to be, you know, not just consulted, but they're at the table. They have a vote. Now, the astronomers have one person on this. I think there are 12 people on this committee. Rich Matsuda, who is the director now of the Keck Observatories, a terrific guy, lived in Hawaii all his life, knows a lot of people, and is on this Mauna Kea Stewardship Authority. So I think we'll have a voice. The Native Hawaiians will have a voice. We know that the chairman of the committee has come to the American Astronomical Society meeting. They came to, and 3 members of the committee came to the American Astronomical Society meeting in Seattle. They talked about the nature of the authority and what they were trying to do, find a Hawaiian solution to the competing interests. And I think there's a considerable hope that that will result in a good outcome. Now, it hasn't happened yet, You need to be patient and honestly quite humble about this because it's a more complicated problem for which PhDs in astronomy are not necessarily extremely well qualified.
That's
But
right.
I think we're doing pretty well. The prospects are NSF is going kind of slowly. They have their own procedure. They want to know what to do, and yes, they got the decadal to tell them, but now they have to do it in their own way. What we would like, of course, is to have enough design and development money so we're really ready to go. And then after you have an evaluation, we can choose whether we go to that site or our alternate site. The alternate site is also in the northern hemisphere, so it has that unique advantage. It's at La Palma in the Canary Islands. It's a place where there are plenty of telescopes. Mauna Kea is our preferred place, and it's higher, it's drier, it's a place where our partners work. So University of California and Caltech are partners in the TMT. They are the people who run the Keck telescopes, the 10-meter telescopes. Japan is a partner. Japan has Subaru telescope, 8-meter telescope up there. Canada is a partner. They have the Canada, France, Hawaii telescope. India is a partner. Well, Hawaii is closer to India than it is to some other places. It has that geographic sort of Pacific partnership quality to it. So anyway, that is the plan for us, is to work with the NSF through the final design, that we're willing to consider, we'll put forth the case for the site we prefer, and we are willing to consider the alternate site. So we want to build this telescope. We want to
Yeah.
do this stuff. I think Hawaii is the right place. I think we have, we don't exaggerate, but we have made some progress. You listen with respect. You take time to hear what people say. We are trying to do the things that they've asked us to do or that they find kind of irritating by the way things were run in the past. So we're really making an effort. And, we have some years of design work still to do. So I hope that there'll be time to work out an amicable solution.
I have to ask you a question that was brought up with Brian Schmidt. Actually, Adam has never talked to me about this in the 3 or 4 podcasts we've done together, but Brian brought it up when he was on about 2 years ago. And he said that one of his regrets was in the supernova discovery time period when you guys were making this just phenomenal observations and exquisite data analysis and so forth, that there was a toxic environment, and he called it a toxic environment. And he felt, in his words, that that some of us, I don't know if that means him and you, or if he's got multiple personality syndrome, but that some of us were not good mentors. And I want to get your reaction because, to be devil's advocate, the fact that there was competition produced great confidence in the veracity of the results once these two competitors basically reached the same results. So do you have any regrets, or how would you have done things differently, if at all? I usually end the podcast by asking a quote based on Sir Arthur C. Clarke, who said that when an elderly, distinguished scientist says something is possible, he's most likely to be right. But when he says something isn't possible, he's wrong. I want to ask you, was there anything wrong? Did you do anything wrong in retrospect? Not you personally, maybe, or Saul, but can you talk about that and what if you had a mulligan? What would you do differently, if anything?
It's interesting. People from the outside say, oh, how great it was that there were two teams, and that when they came independently to the same conclusion, that made it seem more plausible. That's one way to look at it. My own view is that if you have the best methods of analysis and the best methods of taking the data, you're going to get a really good answer. And unless you've made some really stupid mistake, that's sort of the right thing. Whether we should have joined teams, I don't know. I don't think the personalities were commensurate with doing that. But, sometimes people are forced to do that sort of thing. I think that happens in high energy physics. It happens in big experimental things, and where you kind of have to grit your teeth and do it. So I don't know. I feel really good about our team, that We enjoyed working together. It was very congenial, where I thought I should be the boss, but everybody else thought, no, postdoc should be, running the show mostly. So that turned out to be a good thing. And especially because it was a revolutionary result. The fact that I thought this can't possibly be right. Where's Arthur C. Clarke when I need him? This can't possibly be right. That was not the correct answer. So I guess what I would say is I wouldn't really change what we did. I think trying to keep everybody motivated and nobody feeling that their contribution is being ignored or not valued. I think we did a pretty good job on that. And it was kind of complicated, but with some bumps in the road, we did pretty well.
Success, as they say, has many fathers, and failure is an orphan. But you've succeeded so many times in your career, both as a professor, as an advisor, as a mentor, as a scientist, and as an author and real intellect in this field. And I always enjoy seeing you. You're one of those people that just being in the room with you really lights me up. And I'm just so grateful to have people like you in the field to look up to and learn from. And I really can't wait to see what comes from the TMT. We have Shelley Wright here and UC San Diego, who's making heroic contributions. And as I said, this is going to be really a capstone, maybe the last great large observatory of the 21st century. It's hard to believe that, but by the time these things come online after the heroic work of you and your colleagues,
there's going to be that big. They're looking for building that big habitable worlds telescope, and by golly, that looks like the TMT on a sunshade.
That's right. Never underestimate the kind of magical ideas that my colleagues and your colleagues will come up with.
Yeah.
Bob Kirshner, Dr. Bob Kirshner, Barbara Kirshner, thank you so much for spending so much of your time with me and my audience. You're a fan favorite, and I can't wait to see you again in person. And next time I'm up in Pasadena, I'll have to pay you a visit, or you're down here. Please feel free to stop by the observatory, and we'll swap our war stories.
Great, Brian. It's always nice to see you. Thank you for allowing me to do this exploration of my ignorance.
So much fun. If you watched all the way to the end of this episode, I know you'll love this episode I recorded with Adam Rees, who's one of Bob's most notable students. I had the honor of interviewing him multiple times, including here at UCSD. I know you'll enjoy it. Click here.